We're getting to the end of our class on the Introduction to Mechatronics. We spent a lot of time talking about programming a PIC microcontroller and building some simple circuits. Let's talk about the mechanical aspects of mechatronics, usually done by talking about motors. So for the next few lectures, we'll talk about specifically the construction and equations that govern the brushed DC motor. The idea here is that we want to take electronics and turn that into mechanical motion. We'll do that using the Lorentz Force Law. The equation for that is that the force vector is equal to the cross product of current and magnetic field, scaled by the length of our conductor. So let's say that we have a wire, and the wire is our conductor. And I don't know, for some reason, we've put it in a magnetic field. So I've got a north magnet and a south magnet, such that that means there are magnetic field lines going from north to south. So that's our field line B. And I will put current through this conductor. So going into this wire is some current. And I can use the right-hand rule for the cross product to see which way the force will be on this wire. So to do that, you put your index finger in the direction of the current, and you put your middle finger at a right angle to the index finger, going in the direction of the magnetic field, and then our thumb points in the direction of the force. So this means that I should have a force being applied downwards on this wire. So just the fact that I put a wire in a magnetic field, put some current through it, means that I get this magic force on the wire. Our goal is to turn that force into something that's controllable. So if we can control the current in this wire, we can control the force on it. And maybe we can turn it into a reciprocating force so that we get rotational motor. A rotational motor, or a rotational velocity. So how can we do that? The first step would be, let's turn that conductor that's going into our magnetic field into a loop so that it goes out of the magnetic field and pops back in again. So the current goes in, and then the current comes back out again, inside of our same north and south magnetic field. That means we'll get a force downwards on this part of the wire, and an upwards force of the same magnitude on that side of the wire. Let's try to put this on some kind of rotational bearing, and we'll look from the end on. So from the end on, we've got our wire going into the board and our wire coming out of the board inside of our magnetic field. And somehow we've rigged this up so that they can rotate about this pivot point. So initially, when we put current into the board and it comes back out of the board through this loop, we get a force, a downwards force on this wire, and we get an upwards force on that wire. And because we've somehow mechanically tied them to this pivot point, that means we'll get a torque about that pivot point. We can try to plot that. So we get a torque versus angle plot. So the angle would be what is, say, like this angle. And that would be a sine wave. Because at some point, these will start to rotate, but they'll get stuck in this position. So we'll have that wire and this wire going into the board. The force is up and the force is down. And if we were to take these and rotate them this way, the force would pull them back that way. And if we take them this way, the force pulls them back that way. So that would be the force versus angle plot we see here. The trick is, if we can somehow get the current to change direction. So sometimes we get current into the board, and sometimes we get current out of the board based on the angle of the thing that spins here. We call that the rotor. We can get all positive torque. So we'll get the absolute value of our sine wave. So we'll no longer have any negative torque. And what we can see here is that sometimes we get zero torque because we're at this maximum and minimum position here. So what if we coupled this loop of wire with another loop of wire that was like here and here? So this wire loops around back to that wire. Then we could get an out-of-phase sine wave that would produce its own torque that looks like that. And then we could keep adding more coils so we get more and more of these sine waves. The total amount of torque that would come out of this rotational coil system would be the sum of all these. So way somewhere up here would be the sum of those sine waves. And you could see what we have is we have torque, almost a constant amount of torque versus angle, based on the ability of putting current into the coils. And this isn't constant, really. There's some ripple. So every motor that we build is going to not have constant torque with angle, but we'll approximate it as constant torque with angle. And the amount of torque will be proportional to the current. So the question becomes, how do we control the current that goes through these coils so that we only get positive amounts of torque? Because we know we need to be able to flip the direction of the current depending on the angle of the rotor. That's where the brushes come in. So you might be familiar with a brushless motor, the kind of motor you'd see on a quadcopter, or a stepper motor, the kind that would come on a 3D printer, or a lot of other positioning systems. Those types of motors directly control the voltage going to these coils, which allows them to control the current, and they monitor the position of the thing that rotates to decide when to change the direction of the current. So they have to do that for a brushless motor with a sensor that tells them the angle, and then some kind of smart logic that determines which coils should be on at what time. A stepper motor, you kind of do that blindly, where you assume that the rotor is in a certain position and you just turn the coils on and off. A brushed motor, which is an older type of motor, does it mechanically. It mechanically commutates which coils get the current, so that you don't need any smarts. So this was kind of invented before microcontrollers or even digital logic. So it made it a lot easier to control these motors. So the brushed motors are older than those others. They tend to be a little heavier. You get a little less power, so their power per weight ratio isn't as good as a brushless motor. They tend to produce more heat. It's harder to get out of the motor, so you don't get as much holding torque as you would for a stepper motor. But a brushed DC motor is still probably one of the most common motors out there. And if you add gears to get more torque, and if you add an encoder to get the position, you can do anything you want with a brushed DC motor. So how do we do this mechanical commutation? I'm going to try to draw a picture here. It's not going to turn out well, but we'll see how it goes. So we have the shaft of the motor, and it goes off in this direction. And around the motor, around the housing, is a big semicircular permanent magnet, one with a north face and one with a south face, so that we're still getting our magnetic field. But this would be circular, and they would almost touch at the ends. So now what we need our coils to be inside of this shell, filling it as much as possible so that we're getting as many in and out current lines as we can through the magnetic field. So we've got a wire that starts on one end, and then it does a lot of loops and eventually pops back out. That wire is going to be hooked up to a piece of conductive metal that's on the side of the shaft. So the shaft is coming out of the motor like this, and it's got a long kind of strip of conductive metal glued to the sides so that as the motor rotates, this piece of metal rotates. And that would be one of these loops, except instead of going in and out of the board, it would go in and loop and loop and loop and loop and then come back out again. And that would take up, so if this is the motor shaft, that would take up maybe like a third of the surface area of the shaft. So then we would have another set of coils like that and another set of coils like that, so that the motor shaft is almost completely covered with conductors that we call the commutator, with little tiny gaps so that they can't short. And then pressed up against that shaft would be two brushes. So from end on, it kind of look like this. And they would be designed so that they could only ever touch one or two coils, but they couldn't short by touching too many coils at the same time. And electrically, wires would come out, and that's where we would apply our voltage from a battery or a motor controller. So when we apply the voltage to the coil will act like an inductor and a resistor. Current will flow through. Depending on the speed of the motor, we'll get either more or less current. That current will create a torque, which will make the rotor start to accelerate and rotate. As the torque starts to go down, because the coil is no longer well aligned with magnetic field, this commutator is rotating. So this section would break contact and make contact with this one as it rotates over here, and this one would make contact with this one. So the act of the torque making the rotor spin makes the brushes make and break contact with the commutator segments, applying current to the different coils in the correct direction so that we always get positive torque. So that means these brushes are making and breaking contact with this commutator. They're usually made of like a soft carbon material, which is highly conductive, kind of soft so that they kind of get gouged by the commutator segments and make a nice little rounded edge here. And there's usually physically a spring that's pushing that commutator up against the brush. And these are consumable. They will eventually get worn down, and if you have a very nice brush DC motor, those will actually come out with screws, and you can replace the brushes with brand new brushes. On a cheaper motor, though, they're usually not replaceable, and when they eventually break because they've worn down too much, the motor's dead. So the motor has a certain life to it based on the brushes.